Assalamu alaikum everyone. So today we are going to start 0620 paper 61. It's basically alternative to practical, May-June 2024. Let's start with question number 1. A student carries out titration to find the concentration of a sample of dilute hydrochloric acid. The student adds 25 centimeter cube of aqueous potassium hydroxide to the apparatus labeled A in figure 1.1. Adds a few drops of suitable indicator to the apparatus labeled A. Use burette to add a dilute hydrochloric acid to the aqueous sodium hydroxide and indicator mixture in the apparatus labeled A. Name the items of the apparatus labeled A and B in figure 1.1. So, yes. What is apparatus A?
Conical flask.
Apparatus A is a conical flask. And what about apparatus B?
Volumetric pipette.
Volumetric pipette. Very good. Okay. Now, next part. A student adds the indicator after the volume of 250 centimeter cube of aqueous potassium hydroxide has been measured. Explain why the student adds an indicator to the aqueous potassium hydroxide. Yes.
I cannot see the screen. It's stuck, I guess.
Is it strict?
Yeah, now it's fine.
Okay.
To check for color change.
Yeah, actually, no. Yeah, you are partially right to actually observe the color change at the end of the experiment or at the end point. Basically, we use the indicator to figure out when the end point achieved, when the acid and the base both are completely reacted with each other. So, the color change can be seen at endpoint. Next, name a suitable indicator. Yes,
Methyl orange.
methyl orange
or
or any other
thymophylline.
thymophylline. Yeah, very good. We can use any one
Or
indicator.
phenolphthalein.
No, not phenolphthalein, Abdullah, thymophylline. Phenolphthalein
So, like, when
is
do
the,
you use it?
no, actually phenolphthalein is in the syllabus earlier, before 2023. So in the previous past papers, which are of 2022 and the previous one, you will find phenolphthalein, but now it's either methyl orange or thymophthalein.
Okay, sir.
Now, describe how the student can determine the volume of dilute hydrochloric acid used in this titration. So, yes.
Sure, we can check the initial reading and the final reading on the burette and then minus the final reading from the initial reading.
Yes, very good. So what we are going to do, record initial and final readings from the burette. And then when you recorded it, so volume of hydrochloric acid is going to be final reading minus initial reading. Is this understandable to all of you?
Yes.
Okay. Now, B part. The student observes the color change that occur as they add hydrochloric acid from the burette. State one other thing the student should do as they add dilute hydrochloric acid to the aqueous potassium hydroxide.
They should
Yes.
continuously swirl it.
Yes, very
Stir
good.
it.
No, it's stirring is not the correct word. Stirring when you put glass rod and then you shake that glass rod, that is stirring. So it's better you say swirling because you are shaking the clock either clockwise, the conical flask either clockwise or anti-clockwise to make sure whatever we are adding from the burette in the conical flask, it will be mixed completely. So continuous swirling of flask. Is this clear to all of you? Now, question number 2. A student investigates the temperature change when magnesium reacts with dilute sulfuric acid. The student does 5 experiments. Experiment 1. Okay, so you have to read these information very carefully. Use 25 centimeter cube measuring cylinder to pour 20 centimeter cube of sulfuric acid into a boiling tube. Okay, what is a boiling tube? Do remember that boiling tube is like a test tube, but it has a bigger diameter as compared to the test tube. Use thermometer to measure the initial temperature of the acid in the boiling tube. Record the initial temperature. Add a coiled 5 centimeter length of magnesium ribbon to the acid in the boiling tube. At the same time, start timer. Continuously stir the content of the boiling tube using thermometer. After 45 seconds, measure the temperature of the mixture in the boiling tube. Record this temperature. Rinse the boiling tube with the distilled water. Till here, is this clear?
Yes.
The information that they have provided. Okay, now experiment 2. So we are done with the experiment 1, now experiment 2. 25 centimeter, use the 25 centimeter cube measuring cylinder to pour 25 centimeter cube, 20 centimeter cube of dilute sulfuric acid into the boiling tube. Use 10 centimeter cube measuring cylinder to add 2 centimeter cube of distilled water. So what you did, you have diluted, in experiment 2, you have diluted it with some water. Is this understandable? To the acid in the boiling tube. Place a bung in the boiling tube and invert the tube to mix the acid and water. Use the thermometer to measure the initial temperature and record the initial temperature. Till here, is this clear? Now add coiled 5 centimeter length of magnesium ribbon to the content of the boiling tube. At the same time, start the timer. Constantly stir the content of the boiling tube using the thermometer. After 45 seconds, measure the temperature mixture, record this temperature. Rinse the boiling tube with distilled water. Repeat experiment 2, adding 4 centimeter cube, adding 6. Okay, so see, what is the difference among these? If you see, we have only 20 centimeter cube sulfuric acid and magnesium ribbon. Over here, we have 20 centimeter cube plus 20 centimeter cube sulfuric acid plus 2 centimeter cube distilled water and then magnesium ribbon, right? And in experiment 3, we have 4 centimeter cube of distilled water. In experiment 4, we have 6 centimeter cube of distilled water. In experiment 5, we have 10 centimeter cube of distilled water, and rest of the thing that are 20 centimeter cube and the 5 centimeter length magnesium ribbon, rest of the things are same. So in experiment 1, we use the dilute sulfuric acid. In experiment 2, we increase the volume by adding water. And then in experiment 3, 4, and 5, we further dilute the acid solutions by increasing the volume of water. Till here, is this clear to all of you? Yes, if any one of you has any confusion in the method of the experiment, please ask. Okay. Now, use the information in the description of the experiment and the thermometer diagrams to complete table 2.1. Okay. So if you recall, in experiment 1, we have used 20 centimeter cube of distilled water and 0 centimeter cube of water, isn't it? In experiment 2, we have used 20 centimeter cube of sulfuric acid and 2 centimeter cube of a distilled water. In experiment 3, we have used 20 centimeter cube of sulfuric acid and 4 centimeter cube of a distilled water. Do remember this thing. As you can see over here, it is written 4.0 centimeter cube. So what you guys do in the hurry, instead of writing 0.00, you just write 0, 2, 4. So if you do this, you will get penalized on this and you will not get the mark. So you have to make sure if the examiner mentioned something, so use the same format, use 1 decimal place or 2 decimal place. Now in experiment 4, we have used 20 centimeter cube of a sulfuric acid and 6 centimeter cube of a water. And in experiment 5, we again use the same volume, that is 20 centimeter cube of a sulfuric acid. And now we have used, after 6, 10 centimeter cube of a distilled water. Till here, is this clear to all of you?
Yes, sir.
Okay. Now, so initial temperature, they have mentioned. Temperature after 45 seconds, if you see, what is the temperature reading in the first experiment?
37.
It's 37. So do remember, see, it's 25.0. So you must write 37.0, not just 37. Okay. Then over here, if you see, it's 34. So you are going to write 34.0. Then if you see, so it's 30.5, right?
31.4.
No, sorry. Yeah, thank you. 31.5. Then 30.0. And then
34.0.
27.5, isn't it?
Sir, your screen is stuck.
Okay, just give me a minute.
So now it's black.
Yeah, I'm sharing it again. 1 minute. Yes. Is it visible now?
Yes.
So if you see, first one is 37, second one is 34, third one is 31.5, fourth one is 30, fifth one is 27.5, right? Now, in temperature increase, so temperature increase can be found by subtracting the initial temperature from the temperature after 45 seconds. So it is going to be
12.
37 minus 25. So it is 12.0.
12.0.
Yeah, the first one 12.0. 1 minute. The screen is again stuck. Just give me a minute. Yes, is my screen is visible now?
Yes.
Okay. Now, next, 34.0 minus 25.5. So was it, yes, 8.5?
8.5.
Then 31.5
Yeah, it
minus 25.5.
6.0.
It is going to be 6.0. Then 30.0 minus 26.0.
4.0.
So 4.0.
4.0.
Then 27.5 minus 26.0 is 1.5 degrees.
1.5.
Yeah, the internet is problem. Okay. So see, state which experiment 1, 2, 3, or 5 had the smallest temperature change. So the smallest
5.
temperature change is experiment 5, right? Explain why the temperature change was the smallest in the experiment you have given in B1. So if you see in this experiment, we have a 10 centimeter cube of water along with the 20 centimeter cube of sulfuric acid, right? So now the temperature, the energy which is released is used to heat the bigger volume. So as a result, there is a lesser change in temperature. So if we have a smaller volume, so the temperature change would be higher because now the energy that is released is used to heat the lesser amount of water. So there would be more increase in temperature. Now, but there is a more amount of water there, more volume is there. So that's why the change in the temperature or the increase in the temperature is lesser. So it is because largest volume was heated. Is this point is understandable to all of you? Yes, is this clear?
Yes.
Okay. Now C part, complete a suitable scale on y-axis and plot your results from experiment 1 to 5. On figure 2.1, draw a line of best fit. Okay. So,
So your screen is stuck again.
1 minute. Yep, it is stuck. 1 minute. Let me check. Okay. So on y-axis, we have an increase in temperature, and on x-axis, we have a volume of distilled water. So when the volume of distilled water is 0, the increase in temperature is 12, right? Remember, plot the points with the curve or with the cross. Okay, so first let me label it. Uh, 2, 4, 6, 8, 9, 10. So if I label it 2, then 4, then 6, then 8, then 10, and then 12. See? So it means when there is a 0 degree, when there is a 0 volume of water, distilled water, the temperature raised was 12 degrees, right? Then it is again stacked. Yeah. Just give me a minute. Okay, so when there is a zero amount of distilled water, we have just dilute sulfuric acid, then the wall temperature raises 12, right? When we have added 2 centimeter cube, the temperature raises 8.5. So 8.5 is going to be over here in the middle. One minute, please, everyone. Now, yes, now you can see the 8.5 is a 2.5 box because 5 boxes are 1 unit. So 8.5 is going to be 2.5 boxes. So 8.5 when 2 centimeter cube of volume of water has used. When 4 centimeter cube is used, the raising temperature is 6. So at 4, it is going to be 6. Okay. Then when the 6 centimeter cube has been added, the raising temperature is 4. So for 6, it's 4. Then we have added 10 centimeter cube. So the raising temperature is 1.5 at 10 centimeter cubes. So 1 is over here, 2 is over here. So 1.5 is going to be in the middle. So is the plotting is clear to all of you?
Yes, sir.
And what they are saying, draw a line of best fit. So if we have to draw the line of best fit, 1 minute. It is appearing like a curve. But they are asking to. It's 12, 8.5, 6, 4. Okay. 1 minute. These points are. Let me use the other color.
Sir, doesn't the line of best fit have to be like a straight line?
Yeah, it has to be a straight line. It's not
Okay.
like the curve. So actually the points were not visible with the green thing. So that's why I have.
Okay.
Okay. But the thing, there is some issue. We are not getting the actual best fit line. Because the points are not, all the points are not getting on the same line, right?
Yes.
But the other thing that is very important, if you see, use the graph in figure 2.1, did you use the temperature increase when experiment 2 is repeated with 7.5 centimeter cube of distilled water instead of 2? So it can be only possible that this can be deduced only possible, this deduction, when you made it from the graph, when you made a curve. Because if you make a curve, then you can easily figure out that what is going to happen at 7.5 degrees. So it's better to draw the curve instead of best fit line. And let me go through its examiner report. Because see, you can see over here, if you make a curve, then you can easily identify that when the temperature, when volume of 7.5 centimeter cube has been added, how much volume, how much temperature change would increase. Let me check its examiner report. Just give me a minute. It's a 6-1. So see, because when they are asking you this question, so this can be only identified like this is 7 and this is 7.5. So on 7.5, you can make this. So this can be only identified when you are having a curve.
Sir, how will we know when to make a curve and a line?
Okay, the thing is that most of the time examiner use the term over here that draw the curve of best fit. Or otherwise, examiners say the line of best fit, or examiners say that, draw the straight lines. So let me just, I just want to see what they are saying in. So what temperature we are getting over here? It's around 3.75. It's 3.9. No, it's 2.9. 2.5, 2.6, 2.7. Yeah, it's around 2.9.
Sir, how much range will they give us for this answer?
Sometimes they give you the range and sometimes they tell just the working should be shown on the graph. So if you show the correct working, then they will award you the mark. It's 2024, May, June, 6-1. And the question number is question number 2. Yeah. And it's 2C. It's 22.9 degrees. I'm not able to find the examiner report. I will check, but see, from this you can further identify if they are asking something like this, so it can be done. So it will help you whether you are getting the points on the same line or not. So it is going to be 2.09. Now, next part. The average rate of temperature increase in each experiment is calculated using the equation shown. Okay, temperature increase divided by 4.45 seconds. Calculate the average rate of temperature increase in experiment 1. Give units to the rate you have calculated. So in experiment 1, the raise in temperature is 12 degrees. So 12 divided by 45. Can anyone tell me the answer, please?
0.267.
0.267, right? So
Yes.
the average rate is going to be 0.267, and now units. In the numerator, you have a degree Celsius, and in the denominator, you have a second. So it is going to be degrees Celsius per second. Is this clear?
Yes.
Yes, sir.
Okay. Now, explain why the result of the experiments are more accurate if the boiling tube is wrapped in the cotton wool.
The cotton wool helps with insulation.
Yeah. So
and
it's it act as an insulator, right? It insulates, so it will award you 1 mark, and you have to get 2 marks. So you can further explain. So less heat loss occur.
the consistency loss.
Sorry. Sorry. Clear? Is this clear to all of you?
Yes, sir.
Okay. Now, next part. Explain why a 25 centimeter cube of volumetric pipette cannot be used to accurately measure the volume of distilled water added.
Then maybe because it takes more time.
The
No.
volumetric pipette only measures 25 centimeter cube, and we're using 20 centimeter cube in distilled water.
Yes, very good, Marwa. Because see, 25, it is only used to measure only 25 centimeter cube volume. And over here, we are using the volume that we are using is not fixed. We are using 2 centimeter cube, 4 centimeter cube, 6 centimeter cube, 10 centimeter cube, right? So that's why we are not able to use that. Is this clear to all of you?
Sir, could you explain again?
Yes, 1 minute. If you recall, the pipette has only used to measure just 25 centimeter cube, right? We use the safety bulb to fill it to the mark, and it is just 25 centimeter cube. We can't measure 1 centimeter cube, 2 centimeter cube, or any other volume from the pipette, just 25 centimeter cube, isn't it?
Yes.
So see, and
Yes,
and
sir.
and here we have to record 12 centimeter cube, then 4 centimeter cube, then measure 6 centimeter cube. We need different volumes to be measured, right?
Yes.
Is this clear?
Yes, sir.
Okay. So pipette just measure 25 centimeter cube, and in experiments different volumes were measured. I hope it's understandable now. It's clear to all of you. State one other way in which the apparatus can be changed to give more accurate results. So for the accuracy, we can go for a burette, because burette
Sir,
has a
instead
tap.
of the pipette, what can we use?
Sorry.
instead of the pipette, what can we use?
So we have initially used measuring cylinder, right?
Yes.
And that is approximate measurement. But if you recall the burette has a tap at the bottom, so we can control the volume, whatever volume we want to measure, we can measure and transfer that specific amount of volume. So instead of pipette, we can use a burette. So that in the next part 3, they are asking that how can we make it more accurate? So we can use a burette instead of a measuring cylinder. Yes, is this understandable to all of you?
So I've seen some questions in which they mentioned to use an so I've seen some questions in which they mentioned to use an inverted measuring cylinder.
Sorry, can you repeat?
So like I've seen some questions in which they mentioned to use an inverted measuring cylinder. So can you like tell me in which cases we use that?
When we need to collect the gas, see, with the gas can be collected either using a gas syringe to we record the volume, that how much gas is collected. And sometimes they ask you that the gas is collected by displacing the water. So when we need to displace the water and we need to collect the gas, and that gas, actually we have to record its volume. So we use the water-filled inverted measuring cylinder. So when the gas forms, it displaces the water, and on the scale you can record the volume of the gas that has been collected. It is for the gas collection when we use
Okay, sir.
inverted measuring cylinder filled with water.
Sir, can we use it
Sir.
for a specific type of gas?
Sorry?
Do we use an inverted measuring cylinder for a specific type of gas?
Yeah, the gases which are water insoluble, so those gases are actually collected by displacing a water displacement method, in which mostly, like if you are doing the cracking, so any hydrocarbon gas like methane, ethane,
Okay.
ethene, and sometimes carbon dioxide as well are going to be collected by this way, and hydrogen as well.
Okay.
Okay. Now next part. Sketch on figure 2.1. The graph you would expect if all of the experiments were repeated using a 2 centimeter length of magnesium ribbon instead of 5 centimeter length. Label your line G. Okay. So if we measure, use 2 centimeter cube instead of 5 centimeter cube magnesium ribbon, so what is going to happen? That it is going to the temperature change would be lower, right? So you can draw like this in the exact same manner, which is giving you a smaller increase in volume like this. Is this clear?
Instead of 8.
Sorry?
Can we start from 6 degrees
Yeah, it
Celsius?
can be
instead-
start there. They haven't mentioned anything, so you can start any point showing that obviously when the smaller volume of smaller mass of magnesium has been used, so it is going to give you the lesser increase in temperature, right?
Okay.
Okay. Now, question number 3. A student tests two substances, solution E and solid F. Test on solution E. Solution E is aqueous chromium 3 bromide. So see, they have told you what ions are there. So it means it has a chromium 3 positive ion and bromide negative ion. Solution E is divided into two portions. Record the expected observation. In the first portion of solution E, the student adds aqueous sodium hydroxide dropwise and then in excess. So you have to write the observation while when dropwise and when in excess. So you can check over here. See, sodium hydroxide, chromium 3 positive. Green precipitates soluble in excess, right? So I'm going to write the same thing. Green precipitate soluble in excess. Is this understandable?
Yes, sir.
To the second portion of solution E, student adds about 1 centimeter cube of dilute nitric acid and a few drops of silver nitrate. So what we have bromide ion. So if you see from the chart at the back, bromide, dilute nitric acid and silver nitrate both are added, and what we are getting cream precipitate. So the same things are mentioned and we are getting cream precipitate. There is a bromide, so I'm going to mention the observation that we are getting cream precipitate. Is this clear? Yes.
Yes, sir, it's clear.
Okay, now test on solid F. Give me a minute, please. Okay, now table 3.1 shows the test and the student's observation for solid F. Test 1, heat about half of the solid F in the boiling tube until there is no further change. So see, what is the observation? The white solid forms a colorless liquid. The steams come out from the boiling tube and condensation is seen at the top of the boiling tube. After a while, the colorless liquid becomes white solid. So see, as we are observing the condensation and the steam coming out, so it means it is a hydrated, it contains water in it. Water of crystallization. Is this clear?
Yes, sir.
Okay.
Yes.
Now, test 2. The remaining solid F is dissolved into a water to form solution F. Solution F is divided into three portions. To the first portion of the solution F in the boiling tube, add aqueous sodium hydroxide dropwise and then in excess. No change. Warm the product and hold the damp red litmus paper at the mouth of the boiling tube. The damp red litmus remains red. So,
No
what does
ammonia.
no ammonium ion? Very good. So, if you see, whenever we add sodium hydroxide, we are going to get any precipitates. And if no precipitate, then on heating, ammonia is produced and ammonia is tested by this. But you see, the red litmus is not turning blue, it is staying red. So it means what we have concluded from here, no ammonium ion is present. Is this clear?
Yes, sir.
Okay. Test 3. To the second portion of solution F, add 1 centimeter cube of dilute nitric acid followed by few drops of barium nitrate. We get the white precipitate. So what we have added, dilute nitric acid and barium nitrate. So see,
Sulfate.
yes, very good. Dilute nitric acid and barium nitrate. We are getting white precipitate. It means what is there? Sulfate ions are there. So here from this, we have identified that there is a sulfate ion. Now, next one. Test 4. To the third portion of solution F, add a few drops of acidified potassium magnate. The solution becomes light purple. It means what we know that potassium, okay, light purple. So obviously it's a colorless solution, and adding few drops, the whole purple potassium magnate is in purple in color. Just give me a minute. Okay, so the solution becoming light purple indicates that no reaction occur. Otherwise, it goes from purple to colorless. It decolorizes, right? So no reaction. And if no reaction, so it means no reducing agent is present, because potassium magnate is added, always added to identify the reducing agent. That is from the theory of the redox. Okay, now the observation in test one shows that solid F is hydrated. Yeah, that's what we have identified. Describe a chemical test to show the condensation at the top of the boiling tube contains water. So what we are going to do to do this, we are going to use anhydrous copper 2 sulfate, which changes from white to blue, right? To test the water, what we use? Anhydrous copper 2 sulfate. And the results are white to blue. Is this clear to all of you?
Okay, sir.
Okay. Now, D. From the test and observation table 3.1, it is not possible to identify the cation in the solid F. Yes. Give another test that can be carried out to help identify the cations in the solid F. Yes. Can anyone know any other test? Yes. So see, over here, we have used sodium hydroxide and we are not going to get any color. There is aqueous ammonia. So probably if we are not getting any color with the aqueous sodium hydroxide, so with aqueous ammonia, we are not going to get any color. So in this way, the best way to figure out the cation is flame test. See, because flame test is always for a cations, right?
Yes.
So we are going to do flame test to identify the cation. Okay. Now identify the anion in solid F. So we have identified over here the anion is sulfate ion, right?
Yes, sir.
So I hope till here it's clear to all of you.
Yes, sir.
Okay. Now question number 4. A mixture contains 3 compounds: liquid ethanol, solid sodium carbonate, and solid zinc carbonate. Table 4.1 gives some information about these 3 compounds. Okay, ethanol is soluble in water. Sodium chloride is soluble in water and insoluble in ethanol, and zinc carbonate is insoluble in both. Now what they are asking, describe how to obtain a pure sample of each of the 3 compounds, ethanol, sodium chloride, and zinc carbonate from the mixture. So you need to separate them, right? You are provided with the common laboratory apparatuses. So, if you see, you have a liquid ethanol and these two are solid. So, it's very easy to obtain ethanol filter the mixture and ethanol is obtained as a filtrate, and in the residue we will have both the solid carbon, sodium chloride and zinc carbonate. Is this understandable?
Yes, sir.
Okay. Now we have to separate zinc carbonate and sodium chloride. And you see, zinc carbonate is insoluble in water and sodium chloride is soluble in water, right? So we can obtain zinc carbonate. So to obtain zinc carbonate, add water to the residue and stir. So on stirring, what is going to happen? Sodium chloride is going to be dissolved and zinc carbonate stays undissolved, right? Now, filter zinc carbonate is obtained as a residue and is it's water insoluble, so wash with distilled water and try the solid zinc carbonate. So after this second filtration, filtrate is the solution which is passed through the filter paper and collected at the bottom. Filtrate contains sodium chloride, right? Till here, is this clear to all of you?
Yes, sir.
Yes, yes, clear.
Now, heat this filtrate to remove water and obtain solid sodium chloride. Is this clear to all of you?
Sir, shouldn't we say heat till the crystallization point?
Actually, it is already there. We are not preparing it, right? So we are just separating it.
Okay.
If we have to separate hydrated, any compound hydrated means having a, which must have a water of crystallization with it. So we are going to heat till crystallization.
Okay.
Okay. So we are done with the paper. And tomorrow we are going to do the O-level 5070 ATP paper, inshallah. And I will share the timing. Probably the timing will be around 7:30 for tomorrow. Okay.
Okay, sir.
Okay, so see you everyone tomorrow. Till then, take care. Goodbye and Allah Hafiz.